Thank you so much. Thank you all for having me. Thank you all for taking the time to join me today. So let's dive into SQL Server IO to improve T-SQL performance. All right, so if you don't know who I am, my name is Andy. I'm a principal solutions engineer with a company called Century One. But the key things to know about me is that I'm a former DBA and DB developer. I've been working with SQL Server for a very, very long time, and all the different presentations I do over the years, come out of a lot of the different experiences that I've had in the trenches. The other most important thing to keep in mind or to note on this particular page is my contact information. My Twitter handle is up there. My personal email address is up there. I love to talk to people. I love to help out. I mentor people even. I have an entire presentation about getting into speaking and doing this type of thing. So if don't hesitate to reach out, to engage. I love to have conversations. I love giving back to the SQL Server community, and that's part of why I am here today. All right, so enough about me. So let's set the stage for this presentation first. So I like to use analogies a lot. And today we're going to be using an analogy of moving house. I don't know about any of you guys, but I had to move house a couple of years ago, and it was a non-trivial endeavor. I've accumulated a lot of things over the years, even though I've pared down. It was a huge, massive undertaking. And unlike, my younger years where I would just hire some friends and bribe them with pizza and stuff, this time around I hired some professional movers. So with these professional movers, you're going to be giving them tasks of, hey, I want you guys to go pack up my kitchen and pack up my office space and so on and so forth. And in my case, I worked with a specific mover foreman, the man in charge of all the team of movers, right? So I was giving my instructions to the foreman. And then the foreman would then go and give more specific instructions to his movers. Okay, I want you two guys to go tackle the kitchen and pack up all of Andy's belongings to the kitchen. I want you to go pack up his office, so on and so forth. And then the movers would follow the instructions of the foreman, and they would pack up all my belongings, right? So here's the thing. For major undertakings like moving a house, we're all going to spend a lot of time planning, and hopefully everything comes together and nothing goes wrong. But most of us know the reality of things. Things always kind of go sideways a bit, or things don't go as planned. And when things don't go as planned, it costs you time, and time costs you money, especially if you've hired movers, because at least in the United States, you pay movers by the hour. So that can be a lot of money out of your pocket unexpectedly. Well, as analogies go, the same also goes for SQL Server. Time can also cost you money as well. So have you ever, in the context of SQL Server, thought about these different types of questions or been asked these types of questions? Or thinking back to the whole time is money, when was the last time you were on an application or a website and you had to do something, but you got the spinny circle of death as you were waiting and waiting and waiting for something, and maybe you got impatient and decided to go do something else? In today's day and age with the internet and technologies that we work with, our attention span and our patience limit is very, very, very low. Sometimes you only have a few seconds before you risk disengaging a potential customer or audience member. So that being said, performance and responsiveness can be very, very critical to making sure that you and your company and your applications are making money. So to all that and to the questions that you saw before, I want to talk about SQL Server IO to help you really kind of understand what's going on behind the scenes. So here's today's agenda. First, we're going to talk a little bit about storage engine internals, and we're going to talk about the query lifecycle. And then I'm also going to give you an overview of data structures within the storage engine. And then we're going to talk about navigating heaps and indexes. And then that'll be the first half of the presentation. The second half of the presentation will be all T-SQL and IO scenarios. So the second half is all demo. So this is the ultimate goal. I want to kind of level set and present that out once again. Do understand that even though I mentioned the word internals, this is really geared to be a 200 to 300 level session with a splash of 400. Most people, when they hear the word internals, freak out and think this is going to be a crazy 400 level session, but I'm trying to bring it back down to, those of us who are not necessarily operational DBAs, but more like DB developers who happen to just write T-SQL. Maybe we don't, get into the weeds of how does the storage engine work? And my hope is that through this presentation, you at least get a working knowledge of the storage engine. I don't expect anyone to walk out of here to become a super guru in the storage engine, but just to have that exposure, that understanding, just like an auto mechanic or a car enthusiast. A car enthusiast may not have the same level of knowledge about the engine to be able to tear apart an engine like an auto mechanic might, but they have that working knowledge of it such that I understand now when certain things happen, I can squeeze extra horsepower or performance out of my car. So in the same way, we're going to approach the storage engine in that same regards. So that's the agenda, and let's get going. Chapter 1, internals, and let's talk about the query lifecycle. So I said earlier that I like analogies, and I presented this initial analogy of moving house to you. So when you present the task of pack up my kitchen, pack up my office, that is the effective equivalent of a T-SQL query. Select from blah, 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 inner join, blah, 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 so on and so forth. And then when the foreman, the mover foreman, starts giving instructions to the movers on how to actually go about packing up the kitchen, that's essentially the query optimizer coming up with a game plan. I want you two movers to pack up the plates in this box and so on and so forth. Well, much in the same way, the query optimizer is going to be dictating instructions. And then it's a storage engine that's essentially going to be doing that heavy lifting of executing that game plan that the query optimizer generates. So that's kind of the loose analogy that and how it translates into SQL Server. All right. So within SQL Server, what we do is, again, we give SQL Server T-SQL queries. So the important thing to understand from this particular query is that we're pulling data from two different tables, Table 1 and Table 2 in this particular simple example. The other key detail to understand in this example is that we are running this against a cold SQL Server, meaning that nothing else is run against it. And the key detail here is that the buffer pool is empty. Remember that the buffer pool is the area within RAM that SQL Server stores data pages. It's essentially a caching mechanism, but it's also our workspace. That's kind of how I like to describe it. Okay, so I have this T-SQL query. I send it into SQL Server, and first it goes to the query optimizer. The query optimizer does a whole bunch of different magic, and what comes out of that query optimizer is an execution plan. And that execution plan is passed over to the storage engine. The storage engine has many different components to it, but the one that I want to focus on today is called the buffer manager. It's the responsibility of the buffer manager to ask and find, do I have the data available that I need? First of all, it'll go inside and check the contents of the buffer pool. Do I happen to have Table 1 and Table 2 data pages inside the buffer pool? Yes or no? Remember I stated earlier that this is a cold SQL Server with a cold, empty buffer pool. Therefore, the buffer manager must now go out to disk and say, okay, because data pages for Table 1 and Table 2 were not in the buffer pool, I must now go out to disk, retrieve them, bring them into the buffer pool. And then we can start processing the query and processing the data pages in Table 1 and Table 2. So understand that it's that particular process that the buffer manager goes through. Now, if thereafter I immediately execute this second query, Table 1 inner join Table 3, remember we got data for Table 1 and Table 2 in the prior query. So now once again, the query is sent to the query optimizer, and then the buffer manager does its work of looking inside the buffer pool. Do we have data for Table 1? Well, yes, we do, because we pulled it in during the execution of the prior query. But for Table 3, we must still go out to disk, do additional disk I/O, and get that data back. So the way this all translates into SQL Server is if you, for example, look in the Messages tab or in properties of your execution plans and such, we have a metric called logical reads and physical reads. And sometimes when I'm talking to people or folks who don't really understand the nuance of the storage engine, or in talking to people who are more concerned about performance or a performance scenario, they're more concerned about, are we doing too many physical reads? Are we doing too many logical reads? So on and so forth. But a lot of folks don't fully appreciate how the two of them relate. Also, we live in a day and age now where our production SQL servers have a heck of a lot more RAM than they used to, as opposed to 10, 15, 20 years ago, when our SQL servers were much smaller in size. So our buffer pools were correspondingly much smaller. So, it's really in our best interest to, always try and minimize those physical reads, but at the same time, oftentimes we don't have to worry about it as much. We also have much faster flash storage available to us as well. But one key detail, though, is that a lot of folks don't fully appreciate that logical read or physical reads are essentially a subset of logical reads. What do I mean by that? Let me show you. So let's first go back to our analogy, right? So let's pretend that the movers have packed up my entire house. I'm standing inside an empty room. And then suddenly I'm like, well, wait a minute. I need something that you guys have already packed. Where did you guys pack it? Well, we think we packed it with the kitchen. So the kitchen, there's 5 boxes of stuff from the kitchen. So the movers have to go out to the truck and get those 5 boxes and bring them back into the room. And then I can open up those boxes and examine them. So the act of them going out to get those 5 boxes from the truck is equivalent to the physical reads of pulling in those boxes. And then the act of me opening and examining the contents of the boxes are the equivalent of logical reads. Okay, so I find item X. However, and I now have 5 boxes in the room that I'm standing in, but then I realize I need to find a different object. I need to find object Y. Well, I think it's either in these kitchen boxes or it might be in the boxes for my office. So you know what, movers? I need you to go get some additional boxes for me. So they go back out to the truck. They retrieve 3 additional boxes, the ones that correspond to the office. That's another 3 physical reads. But then I must examine all 8 boxes, the boxes from the kitchen and the boxes from the office. So this example will hopefully better illustrate how physical reads are essentially a subset of logical reads, and you could have a lot or a few depending on whether prior queries brought those boxes into the room already, right? So while you may have physical reads under one scenario, you may not a few moments later, again, depending on what other workload is going on, who else is making similar kind of requests for those same data pages, and so on. So some key takeaways that I just kind of want to reemphasize and reinforce from this little chapter is that physical reads are slower than logical reads, and it's additional work that we must do. Again, while we happen to have much faster physical storage these days, like flash storage and stuff like that, reading from RAM is always going to be faster. And under ideal conditions, we want to be doing buffer pool I/O whenever possible. But keep in mind that all work is to be executed against data pages in the buffer pool. I've talked to some people who are under the misconception of, okay, I'm doing those physical reads. I still have to reread those pages logically in order to, again, examine the contents of them. The physical read is fundamentally the retrieval of that into the buffer pool. So keep that distinction in mind as a key takeaway. Okay, so that being said, let's move on to talking about those boxes. And that's where we're going to talk a little bit about data structures. So a lot of folks, when they see a query like this, select top 1 from table 1, will think that SQL Server will only pull back 1 record. But from an I/O perspective, the smallest unit of work or the smallest object that SQL Server can work with, if you will, or must retrieve from an I/O perspective is a data page, one of those boxes, going back to the analogy. And a data page is an 8 kilobyte construct. That's why I like the term boxes, because a box can contain many different things, right? So this is a quick overview of what a data page happens to look like, but understand that these are 8 kilobyte fixed constructs within SQL Server. And when you talk about logical reads, that is the unit, or I should say, that is the number of data pages that were read logically. So whenever you see logical reads, say 1,000 logical reads, you can multiply that 1,000 by 8 kilobytes, and that's the volume of data that you essentially had to process from the I/O perspective. So most of us don't deal with one single data page, though. We create tables such as this one. This is just a very simple table here. Notice that it does not have a clustered index on it. That being said, the result of this is a heap. And a heap looks like a logical string or a logical linked list of data pages. I'm not worrying about the physical and how this is actually laid out on a disk. That's a different discussion and outside of the scope of today. But this is what a heap looks like from a logical perspective, a linked list of data pages. And it's all completely unordered, okay? Now, if I want to bring order into the world, I can add in a clustered index. So in this case, I'm just going to create a clustered index, and that will take that heap and transform it to a completely different kind of structure. And that structure is something called the B tree. B tree in this case stands for a balanced tree. Many of us were introduced to the concept of a B tree as a binary tree, but in this case it is a balanced tree. And this is essentially what it looks like. Also, if you create any non-clustered row store indexes, they will also take the form of a B tree structure. Column store indexes are outside of the scope of today's discussion. That's an entire presentation in and of itself. But for row store, non-clustered index, or the clustered index, which is essentially the base table, as I also like to describe it, will take the form of a balanced tree and look something like this. So now let's get into the internals of what these trees look like and what these heaps look like and how we go about navigating and finding data within them, okay? So one important thing to understand first and foremost about T-SQL is the nature of the language. And this is something that I find, is very enlightening for folks who are not DBAs by trade. Maybe there are folks who, get into our industry by accident or who are developers, like application developers, who happen to also write T-SQL. So whenever you have a T-SQL statement such as this one, remember again that it's passed to the query optimizer. And the query optimizer comes up with an execution plan. Because here's the thing, that execution plan is what actually contains whether I'm going to do an index seek or an index scan or a nested loop join or a hash join. The physical operators, exactly how, exactly what am I going to be doing or how am I going to be getting the data? The key distinction is that T-SQL is what's called a declarative language. A declarative language, the code says, what do I want? I want data from table 1 and table 2, but I'm not telling SQL Server how to go retrieve it. I'm not telling SQL Server, I want you to do an index seek here or to do an index scan here, right? It is up to the query optimizer to come up with the execution plan, much like my prior analogy, where it's the mover foreman who comes up with the game plan. You do not dictate the execution plan. Yes, there are ways to cheat using hints and things like that, but we're not talking about that. We're just talking about how things are normally handled. But this distinction is very important because many folks who have like a computer science background like myself or traditional application developers are used to procedural languages where the code also dictates how to go about doing something, whereas T-SQL does not. And that's something that you need to shift your mindset a little bit to understand that SQL Server and T-SQL is a declarative language and therefore has implications. All right, so that being said, let's take a look at, first of all, at the customer table. So this particular example table is a heap. There's no clustered index on it, right? So it's going to look something like this. Remember, it's a logically linked list of data pages, and there's some random sample data inside of it. But understand that all of these different data records are completely unordered. I have no idea where anything is. Even if you try and insert all of this data in an ordered fashion to SQL Server, it's unordered data still, because it still has no idea what is where, and there's nothing enforcing ordering within a heap. Now, on the other hand, I could change things around and add in a clustering key. I'm going to add in customer ID as a clustering key. And then actually for the next couple of slides, for simplicity's sake, I'm also going to use a non-clustered index. In this case, a non-clustered index on the last name and first name. And then I'm going to include two different columns, first visit and email, to make this a covering index because, a good chunk of my workload also needs those two data points, but I don't need to seek or scan on them. So if you want to learn more about covering indexes and included columns, that's a completely separate topic in of itself. But understand that an include column is meant to kind of help you to avoid a certain type of operation, which we'll cover in a moment. Okay, so let's take a closer look at the index B tree structure. Once again, we're going to use that non-clustered index here. So at the top, we have the root level. In the middle, we have 0 or more intermediate levels. In this case, we only need one intermediate level. And at the bottom, we have what's called the leaf level. So let's take a zoom in a bit and take a closer look at each of these different levels. So first of all, you have the root level, and here's sample data within. I have 3 records in my root level. Again, remember it's the last name and the first name, and then that number in this case is the clustering key. In this case, my customer ID, which was an auto-incrementing integer, okay? So in this case, I just happen to have these 3 values in the root level. So now let me show you the root plus the intermediate level. So I'm going to show you the first 2 data pages of the intermediate level. And notice an interesting relationship. The first record in the root level is now the first record in the first data page of the intermediate level. And the second record of that value there in the root level is the first value in the second intermediate data page. And then, if Simon Paul would now point to a third data page in the intermediate level. So this would essentially be, you can think of these as pointers, if you will, to that very first value. But knowing that those are the first values on a given page, I now have boundaries set, and that's the key. So I know that if I'm looking for a value where the last name is, say, begins with the letter D, it's going to fall between Adams and Martinez. So I know I need to go to that first data page. Otherwise, if I was looking for a last name that starts with the letter P, then I know I need to go to the second data page because that falls after Martinez but before Simon, for example. Okay, let's take a look at that first intermediate level page and then the final leaf level pages. Here's the first two of them. So again, we follow the same methodology where that first record points to the first record of the corresponding leaf level page. The second record on that intermediate page points to the second page, that very first record. But notice on the leaf level, there's additional data points here as well. The value's first visit, which is a date, and then the email address as well. This is where those included columns are manifested. So you can't use the included columns to help you in navigation, but it's there as a reference point if you're using them or if you are querying them as part of your select clause within the course of your T-SQL statement. Okay, so let's first take a look at trying to query a heap. So remember that a heap is completely unordered data. So if I have this simple select statement where I'm selecting from customer where last name is equal to Dean, how am I supposed to find that? I have to do a full table scan. I have to search the entire thing. Even if I find one record where the last name is Dean, I could have more. So the way we count the work that is done is that SQL Server must scan each of these data pages. So the cost of this from an IO perspective is 8 logical reads, okay? Now, what if we are going to scan my non-clustered index? Well, again, I'm doing this simple select, but note in this example, there is no predicate. It's just a select blah, blah, blah from customer. So to do this, we will first navigate to the root, and then we will navigate to the first intermediate, and then to the first leaf level. And then we do a complete scan across. This is a full non-clustered index scan, but we must always go to the top of the tree and then navigate on down. And this is a hair bit more additional overhead. As you can see from a logical read perspective, 10 data pages rather than 8 data pages. So just a hair more expensive. On the other hand, a non-clustered index excels when we need to do seek operations because now I am seeking, or my predicate is looking for last name is equal to Dean. So now I can once again go to the root. Dean happens to fall between Adams and Martinez, so I know to go to that first intermediate page. And I look at Dean and see that it falls between Chavez and Howard. So now I know I need to go to that second leaf level page, and now I found my record. And in this case, logical reads only 3 data pages. That's a heck of a lot more efficient. That's good. One simple or one simple example as far as why seeks are better than scans. Now, what about this particular example where last name is greater than Inez and last name is less than Sark? Do you think you're going to seek here or are you going to scan here? Actually, we're going to get kind of a hybrid. We start out with a seek. So we're going to seek on the lower of the 2 values, Inez, and then we're going to do what's called a range scan. SQL Server is smart enough to basically only scan a subset up until I hit the point where I find Sark. So in this particular example with this range scan, we do 6 data pages of work, okay? Now, in this example, I've changed the predicate slightly. Remember that the non-clustered index is defined as last name, first name. And in this example with this T-SQL query, I'm going to query where first name is equal to Arthur. However, I don't know what the last name is. I just want all records where first name is equal to Arthur. Is it possible for me to navigate this tree to find Arthur? The answer is no. I must unfortunately do a full index scan here. And I can't necessarily stop in the middle because I could have many records that are where Arthur happens to be located instead of just one in this simplistic example. So I must do a full index scan. In this case, again, 10 data pages is what our cost is from an IO perspective. Now, there's an interesting thing out there where I keep hearing from folks that seeks are always better than scans. I've even heard some folks go so far as say if they see a scan inside an execution plan, they must reformat or optimize it to transform it into a seek. And unfortunately, seeking is not always better than scans. And that paradigm comes up a lot, especially when you use this particular approach of an in clause with a couple of different strings, where last name in these, what, 6 last names that I happen to have here. So what's going to happen here is that SQL Server is going to seek on the first last name, Alan, but then it's going to do another seek on Chen, and another, and another, and another. So all said and done, it's going to do 6 individual seek operations. There's no way to say from maybe if I've done the seek to Alan to try and jump around on the leaf level, I must always start from the root level and seek on down. So because of these subsequent seeks, the total work that must be done is actually 18 data pages. So depending on what's happening, this is a common reason why you might have an index and you say, well, wait a minute, I have this non-clustered index here, but why is SQL Server scanning? Because a full table scan or full index scan, in this case, is a heck of a lot cheaper, 10 data pages as opposed to 18 data pages if I were to do individual seeks here. So again, a simple example of seeking is not always better than scanning. Sometimes you're better off just scanning the entire thing. All right, so this select statement I've modified by, we're going to look for first name, last name, first visit, city, and state. Was city and state part of the definition of our non-clustered index? It was not. But because I have this predicate here where last name is equal to Huang, I can still do a seek on this particular non-clustered index, and I can find the record in question. However, I need 2 additional data points, city and state. So because of that, now I need to go back to the clustered index or the heap, i.e. the base table, in order to get those additional 2 data points, city and state. So this is extra work and extra I/O. So the key lookup operation is something that can also really, really burn you from a performance perspective because an index doesn't fully cover the query in question. So let's just do a quick recap of some of the highlights that I just talked about as far as index operations are concerned. So hopefully you have a better appreciation that key index order does matter and that we can only seek on the leading key column if that's available to us. Remember the first name and last name examples, right? And that adding appropriate columns to included columns will help you cover a query. That's what will help you avoid a key lookup operation. And then hopefully you have a better appreciation that seeks are not necessarily better than scans. You want to check the properties in the execution plan. So with that, I'm going to pause here for some questions. I see that there are a few that are popping up. Otherwise, we've kind of concluded the lecture portion. So let's see what we happen to have in here. So how do we tackle an in clause with 6 individual index seeks? That's a really good question of how you would tackle that. You could potentially put those data points into, say, a temp table and do a join or an existence. There's a number of different ways to rewrite that. But hold that thought because one of my demos actually kind of explores that a little bit more. Let's see, are there any other applicable questions? No, just some fun comments in the chatter. So, all right. So with that then, I'm going to switch over to Management Studio. If you still happen to have a question, please type it in. You guys all have a moment or two.
There was actually a short question in the chat about is there a particular reason to include IX or NCIX in the index name?
Very good question. Sorry, I missed that. So frankly, that is just a naming scheme that I personally like to go by. I just like IX and I use CIX for a clustered index, but that's just kind of personal preference. So that's all. And Hugo also made a comment that even a full table scan is not always bad. Yeah, absolutely. So again, everything is about trade-offs, right? So, and again, what would the optimizer potentially do otherwise? Would it do 8 bajillion different individual seeks, which again could, further increase the volume of, from an IO perspective. So yeah, again, a full table scan may not be a bad thing because what is the alternative? What else could be potentially happening? So, and I'll let Hugo chime in on the chat with his thoughts as well. So, hi Hugo. All right. So for my presentations, I use a database called the Auto Dealership Demo. For what it's worth, all of these demo scripts, my PDF and the demo database are available up on my GitHub. The last slide of this presentation will have my GitHub URL up there. Okay, so we're using the auto dealership demo. I'm going to turn on set statistics IO, and I'm also going to execute a command called drop clean buffers. What drop clean buffers does is it empties your buffer pool. Please don't ever do this in production because obviously you're going to have a DBA that's very mad at you. But I'm doing this simply for demo purposes. And then I need to turn on actual execution plan. So this is just a simple example just to prove to you what happens when you read with a cold cache. So I'm just going to do a select top 100,000 out of inventory flat. And then in the messages pane, we see that I've done one scan operation. I've done 1977 logical reads, but then I also have one physical read. And in my example, I have actually happen to have a whole bunch of read-ahead reads here. So even though I've done a lot more I/O, read-ahead reads are actually an optimization. It's SQL Server optimistically saying, "Oh, I think you're going to need all of this other data, so I'm just going to go ahead and retrieve that here." But understand that the logical reads are essentially what I needed in the end, if you will, to fulfill those 100,000 records. And then if you look at the execution plan, this is just a clustered index scan. So we're scanning the entire thing. But I have a top operator here that limits me to the top 100,000 records. Okay? Now, I don't have a cold cache anymore. I just ran some code. So I'm going to rerun that same particular query just so you understand the nuances and the differences here. So if I go back to the messages tab once again, I still have the same logical reads. However, now I don't have any physical reads because we already pulled those data pages into the buffer pool here. So understand that simple distinction. But the execution plan is absolutely identical. We still do the clustered index scan as you can see up here. What's interesting is that the execution plan essentially kind of takes the assumption, if you will, that you're always reading off of disk, or essentially it doesn't care as far as where that data happens to reside. That's one of the reasons why the buffer manager and the storage engine is the one making those decisions about where can I find this data. It's not the query optimizer or the execution plan's job in of itself. If you want to check out what's inside the buffer pool, here is a cool little query that you can use. I'm not going to really go into the details of it, but do see that, hey, right now, Auto Dealership Demo happens to have just under 80 megs worth of data sitting inside the buffer pool. I'm going to drop clean buffers, and then most of that data will now be flushed out. There'll still be some residual data because there's other metadata and things like that that's stored also within the buffer pool as well. But for all intents and purposes, we dump the data pages. So that's what that command does. So let's do a quick mixed join example just to kind of show you exactly what's going on here. So I'm going to drop, well, actually, you know what? I'm going to skip this example. This is a very simplistic example. And in the interest of time, I want to move on to some other examples because I have some better examples. But this is the simple example of, table 1, table 2, table 1, table 3, right? So I want to skip this one for now. This is the one that I actually want to do. So we're going to now start comparing, contrasting heaps versus clustered indexes. So I have a table here that's sales summary heap. I have another table here that's just sales summary. If I do a simple select from both of them without any predicates, my execution plan will show me that I have a table scan for the heap and then a clustered index scan for the table that is a clustered index. For the messages tab, logical reads 3106 for the heap, slightly more for the clustered index because I had to look up some allocation pages, and then I had to also navigate the B tree structure. So it's a hair more expensive. However, a clustered index will also, first of all, let's do a quick top one just to show you what happens if I just do a simple top one version of it. This will better illustrate that I actually have to check an allocation page and then navigate the B tree structure in the case of a clustered index, 3 logical reads instead of 1 simple logical read. All right, but not all is lost. What if I happen to have a predicate here? I'm going to search by a VIN number or vehicle ID number to just find a very specific record. Well, in the case of a heap, now I have to scan the entire thing because I don't have, because all I have is this heap here. I have to go find and look through every single possible data page. Whereas in the case of the regular table, I only have to do 3 logical reads because I can seek exactly to the value that I want. Now, how do I know all this, or are you going to trust me and take this at face value? Well, here's the thing: I can quickly show you the internal structure of each of these different tables, and this is where I love to share one of my favorite little quick tips with you: is to make use of the built-in store procedure SP help. So I'm going to run SP help against sales summary, and then I'm also going to run it against sales summary heap. And the result sets you're going to get for each of these two different constructs will show you a whole bunch of different information, such as the underlying columns, their data types, if there's an identity column, or in this case, the clustered index happens to be the VIN number for sales summary. And then if I go to the second half of it, there is no clustered index. I just see I happen to have a non-clustered index on this particular sales summary heap table, right? So this is a really cool way to kind of quickly double check information, because I don't know about you guys, but I don't memorize the full schemas and all the minutia details of all the different tables and such that I have to work against. But here's the thing: making use of this and typing this out every single time is kind of a pain. I'm lazy. So here's a quick tip for you, a management studio tip that I love to share in every single one of my presentations. Go up to Tools, go up to Options, go to General, Keyboard, and then Query Shortcuts. And inside Query Shortcuts, you can map a control number key to any number of different commands. So you see I have a whole bunch here. And if you go search on my blog, I actually have a blog post that talks about each one of these and why I selected each one of these and how I use them on a day-to-day basis. But seeing that SP help is mapped to control 3, if I'm going through some code like sales summary right up here, I can hit control 3 and then bang, I've just executed SP help. So this is one of those things I didn't use not only on a daily basis, but on an hourly basis, because, again, I don't memorize the schema of everything. So one of those quick tips that I always love to share with folks, it's one of those things that I find is extremely invaluable. All right, so let's do a quick range scan example. So I have inventory flat sold price between 30,000, between these two particular values. I'm doing max stop 1 just to limit parallelism intentionally, just because it makes plans and such easier to read. So, oops, I need to turn on actual execution plan first. Let me rerun that. All right, so let's take a look at the execution plan. In this case, I have an index seek operator. But if I look at the underlying details here, I see the seek predicates are actually greater than or equal to and less than type values here. One thing I want to emphasize, though, is that not all the information that you may need or want about an execution plan is available to you in the little tooltip here. I want to encourage you to start spending time in the Properties tab. I can either open it up from the right-hand side, or I can hit F4, which is the query shortcut. And the area that I'm going to jump down to, let me just do this, open them up real fast, and then I'll show you the details and zoom in. Seek predicates down here. Notice I have a start and an end here. So this is what's showing me that I actually did a range scan here. The other thing that also shows me, or the other hint, is scan direction. In this case, we scanned forward. I went to the first value and I scanned forward. So these are the little hints here, even though I see an index operation or an index seek operation, that I truly did a range scan operation. So that's something to check out. All right. So here's a multi-seek example now. So I'm going to turn on actual execution plan once again, and now we're going to seek against customer states. I have 4 states from the United States in my example here. And in the execution plan, against the customer table, I have a clustered index scan. I'm going through the entire table. Well, what's in that customer table, Andy? I'm going to do my quick SP help trick, just to show you that, you know what, right now, right now, in the indexes area, I only happen to have a clustered index on customer ID. I have nothing as far as a non-clustered index is concerned on the state value. So to help me out here, I'm going to create a quick non-clustered index on state in order to support this query. So now I'm going to repeat that. Now if I look at my execution plan, I see that I have an index scan. Or not an index scan. I changed from an index scan to an index seek. However, check out the details. And this is, again, where we're going to revisit the Properties tab. I may think that, oh, good, I have a seek. But if I reopen the seek predicates, I've actually done multiple seeks here 4 seeks. So there's extra I/O, there's extra work that I wound up actually doing in this particular example. By the way, the I/O cost in this particular example, if I look at the customer value here, we did 4 scan operations, really 4 seeks, and it was a total of 145 logical reads. Okay, well, what if I just happen to have one state? Let me just show you that as a kind of a baseline. If I'm only doing one of these from an I/O perspective, that's still going to consume 36 logical reads because I have many values inside the customer table where that state happens to equal Illinois. But just to give you an idea of what one state happens to look like, right? But here's the thing. We all know that the United States of America only happens to have 50 discrete values, 50 states, right? And let's pretend that this environment, that this database only covers the United States of America. So that being said, what if I happen to have, would it make any sense to generate an in clause with all of the discrete states? But here's the thing. Many people work with ORMs like Entity Framework or NHibernate that love to generate in clauses with all the discrete possible values. So if I'm doing all 50 states here, even though I know they're all 50 states, if I have an ORM that's just auto-magically generating code like this, well, then I'll come out to the execution plan, go to the index seek, go to the seek predicates. Look how many seek predicates I happen to have. We did 50 individual seeks, even though I know better. I know that I'm already including all of the states. I don't even need that in there. But we wound up doing a heck of a lot of additional work. In this case, if I look at the messages tab, scan count is 50, 1,809 logical reads. Now, what's the equivalent of just doing a full scan of the customer table? I'm just going to do a select state from customer, which will do a full scan of that non-clustered index that I created. So so in this case, 1607. So that's a difference of about 200 logical reads. So this is a simple example where a full scan was better than than all those individual singleton seeks. So this is an anti-pattern to kind of watch out for, especially if you live in an ORM type environment. All right, and going back to that one additional question from earlier, yes, you may want to look into creating a temp table, using an existence clause. There's a couple of different ways you can kind of go about mitigating this. So this is an optional script here. We're going to skip over that in the interest of time, and I'm going to start diving into the individual T-SQL scenarios. Let me just quickly check if there is a couple of questions. Drop clean buffers, is that for the entire SQL Server instance or database specific? Off the top of my head, I believe that is for the entire instance. Please correct me if I'm wrong in the chat. Frankly, I can't remember that detail because I very, very rarely use it. It's just one of those things I use for demo every now and then. What are your thoughts on filtered indexes? Are they always useful? That's a very big, it depends. That's a completely separate discussion. Depends on your workload and assessing things from that bigger picture. But yes, they can be very, very powerful. So I'm not one who discounts them. I will definitely evaluate them if it benefits my workload as a whole. But kind of a different discussion. Thank you, Hugo, for the reinforcement that drop clean buffers does hit the whole instance, but there is a database-specific version of that. So thank you, Hugo, for backing me up. All right. This is why it's awesome having friends and presentations like this. If there's something you don't remember, ask a friend. All right, let's jump into scenario 1. Okay, we're going to use auto dealership demo. Do my quick bit of setup by turning set statistics IO on, and I'm going to turn on actual execution plan once again. Okay, so I have an example query here where I'm querying out of the inventory table, sales history table, customer table, where VIN is equal to a specific VIN number. And we get some information back. And if I look at the execution plan, I have a couple of different operators in here. Remember from the slides, we talked a little bit about key lookup operations. So I do have, a corresponding index seek, but then I'm doing some extra IO here for each of these corresponding index seek. And remember how I talked about a key lookup is essentially additional work, additional overhead that I have to do here. So this is a very simplistic example where my, total logical reads here happen to be only like, 3, 6, and 6 here, right? So not much, but again, I'm only just pulling back, one record here. But what if we are querying in greater volume? What if I'm pulling back many different VIN numbers, as in this particular example? So in this case, I'm pulling back 50 records. In this case, scan count 55, logical reads 600-ish and 400-ish. I'm actually going to copy this out and save it. And then let's look at the execution plan once again. So I'm doing individual index seeks, but I'm also doing individual key lookup operations as well. So this is an example where things can compound one another. So not only doing individual index seeks, I'm also doing a key lookup per individual seek. So these basically all add up, right? So that's something important to keep in mind with these key lookup operations. So let's quickly check what kind of indexes we have on the inventory table, one of the two tables where we have the key lookups. So first of all, I'm going to use SQL Server's built-in store procedure help index. Now, I actually don't like this. And the reason for that is this. Help index shows me the index name, the description, and it shows me the index keys, but it does not show me the included columns. So I could have, these indexes here could have included columns in them, but I have no idea. So this does not help me at all. So instead, I strongly advocate using a version of a help index written by Kimberly Tripp of SQL Skills, SP SQL Skills Help Index. You can just go Google SQL Skills and Help Index. And now that'll give me additional data points, including the included columns. Yay, there's also filtered column information, whatever that filter predicate happens to be, and additional data points. But this is something that I advocate using, especially when you need to look up information about your indexes. Okay, so I'm just going to jump ahead and I'm going to create two covering indexes that will help our two queries in question. So the topic of actually figuring out, whether an index can, cover and that sort of thing, that's a completely separate discussion outside of here. So in either case, I'm just going to be running these particular those two index creations, and then I'm going to run my sample query from before. And let's compare and contrast the IO and what actually happens here. Whoops, I want to turn on actual execution plan. Let me rerun that again. Now that we have the execution plan up here, look at my IO. We had what, 600, 400 or so, something like that. Now we're down to 200 and 165 because I'm doing a heck of a lot less IO. Now these numbers are small, but remember, this is demo code. So this is just, so think in percentages, right? 600 to 200, that's a huge percentage decrease, right? So think about it from that perspective. If I look at my execution plan now, I now just see the index seek operators. I don't see the key lookup operators anymore. So that's really cool. So yeah, I've been able to improve performance a bit by removing those key lookup operations. Now, here's the thing. Many folks, when they're query tuning, will focus in on those big, long queries, those things that run for minutes or hours at a time. And queries like this that still ran very, very lightning quick, a lot of people will oftentimes neglect and not really consider or think about from a perf tuning perspective. But I'm going to start making the argument that you should start thinking about those because many folks happen to have a query like that that's run in tremendous volume, hundreds or thousands of times by our application, or hundreds of thousands of times a minute by our application. So it's not the individual execution you need to be worried about, but it's the sum total of executions. So if you have a fast running query like that random VIN lookup value, and it's run thousands of times a minute by your application because it's a website that helps you look up car information for an automobile dealership, that IO adds up, and it adds up very, very, very quickly. So, so that being said, I have an example here where I'm going to run this stored procedure, which is basically that particular query from earlier. I ran it actually in volume earlier, and there are ways to show you the consequences. Actually, so I am going to cheat here, and I am going to use SentryOne. Yes, I do work for them, and no, I'm not pitching them as a vendor or anything like that. But it's very easy just for me to show you the sum total and the ill effects here. So I ran that piece of code earlier, the SP random VIN lookup, and I can show you from an aggregate perspective the total executions and the total resource utilization. And in this case, 30 million logical reads across just under 1,000 executions, 922 executions. So again, what I'm trying to convey to you is that this adds up fast. And to further prove the point, you can see in the little plan preview diagram, I have my key lookup operators. In fact, we're even referencing key lookups here. I happen to have 2 key lookups in that particular statement. So use whatever tool you prefer to use. And again, I know you can find this type of information in Query Store and DMVs, but this is from a demo perspective, just the quickest way to show you that you need to start worrying about things in volume. That's really the moral of the story here. Don't only focus in on those very long, heavy-hitting queries. Think about what happens from that workload perspective, because that I/O also adds up, and it adds up very, very quickly. Okay? All right. So that's scenario number one. Let me jump over to scenario number two. Okay, so I'm going to do a quick little bit of setup here where I'm going to create a couple of non-clustered indexes, one on the customer table with the state, another on sales history with transaction date, and a couple of included columns here as well. And then I happen to have this particular example query where, we're going to declare a couple of variables, transactions start and end, the state, and then, we're going to just look for, states and the average sell price, joining all these different guys. So, I would expect that because I'm, specifying specific values here, I'm going to expect to see seek operators within my execution plan. So if I jump over to the execution plan, hey, wait a minute, why do I see, hang on, let me pull this up. Why do I see a handful of different scan operators, especially against the customer table? Why am I scanning the entire customer table? I gave it a state, right? And remember, if I was doing a range scan, this would manifest itself as an index seek. So what's going on here? Why am I doing this full scan? Well, the devil's in the details. Whoops. And in this particular case, you see how the select statement here had a little warning symbol. That's because if I scroll on further down, I happen to have a warning about something called an implicit conversion. So this all gets into data types. And when you mismatch your data types, SQL Server essentially has to convert the different values on the side of the query, or side of the equation, I should say, that has the lower of the two data types. If you want to learn more about this, go look up my presentation called Why Your Data Type Choices Matter. That's a full 75-minute presentation about that, and there's various recordings of that available online. But in either case, an implicit conversion, what it boils down to for our talk here, is that an implicit conversion inhibits SQL Server's ability to seek. I must upscale and essentially convert every single customer value and convert that state value. And the reason is the detail here. The state is declared as an nchar2. However, if I look at the customer table by using Control-3, state here is declared as a char2. So a non-Unicode data type versus a Unicode data type. The lower of the two data types must be up converted to match that of the other one. And in this case, the lower one happens to be the char2. So every single value in the customer table must be scanned, up converted, and then it can be equated against this. So this is a simplistic example of how not paying attention to your data types and matching your data types can inhibit I/O and cause unusual behaviors to occur. So if I change the data type over to from state to a char2, I now get the index seek operator that I wanted in the first place. So yay, this is much better. This is much better. This is exactly what I want. And now I'm able to get away with that. So moral of the story is to check out your data types. Now, you might ask yourself, how do I know if I happen to have these implicit conversions hidden in my system, hidden in my workload and such and stuff like that? Well, Jonathan Cahias of SQL Skills has helped you solve that problem. So he wrote a long blog here and has a whole bunch of code that shreds the XML that's stored in the plan cache. So that way you can look at your execution plans that are cached and get a better sense of whether you have a whole bunch of implicit conversions that are occurring in your environment and maybe you don't realize them. So I'm going to run his code here. And I'm going to encourage you to go check out his blog post. He goes into greater depth of how to deal with it and whatnot and how he approaches things. But it gives me, the statement that I ran, I converted from a char2 to an nchar4, what the data point or what the data columns happen to be, so on and so forth. So you can run this. Be careful running it against production because shredding XML is a non-trivial type of operation, but run it against a QA environment, a staging environment, even development, just to kind of, sample your data ahead of time. But remember, it runs against the cache, so you need to run a workload first, hopefully something that's representative of your code, and then you can get a better sense of whether implicit conversions are something that will burn you or not burn, or already are burning you or not. All right, so that's something that you can take away today and go play with. All right. So I have scenario 3 and 4 in here, but in the interest of time, I'm actually going to skip these because I'm going to jump to scenario 5, which is a brand new demo I put together last night specifically for this conference. I'm very excited about this one. I think this is a fun one. Let's see. We're going to do some quick setup here with the dealership demo and turn on set statistics, IO, and time. Okay. So first of all, I just want to introduce to you the data that we're going to be querying, just so that we are all on the same page. We're going to be going against a flattened table called inventory flat. We're going to be grouping by vehicle models. So it's model name, and I'm going to show you the number of models so you can see the data distribution, the corresponding data distribution. And then I'm also going to show you what underlying indexes are defined. So inventory flat has just over 2 million records in it. And each corresponding model has anywhere from like 130 to 150,000 records each. Okay, that's kind of what I'm showing you here, just to show you that each model has about the same number of records, right? There's not a huge discrepancy, or there's not one edge case that only happens to have like one record versus the majority, or anything terribly unbalanced like that. And then finally, I'm going to show you the non-clustered indexes that I happen to have defined down here. Fundamentally, the one that we care about is model name, inventory flat ID, and the other included column is the VIN number. Okay, so here's my example query. So oftentimes, like inventory flat is a very wide table, and oftentimes we have those those queries where we need almost every single column in that table, or maybe we legitimately do need every single column in that table. So that's kind of what I'm doing here. So we have the select statement give me pretty much almost every single column inside that table, where model name is equal to RAV4. I'm using option max.1 just to limit parallelism, just for example purposes. So let's see what this guy happens to do here. So first of all, let's look at the execution plan. This is a clustered index scan, and I'm scanning.
Andy, I think we lost your voice. It looks like he's figuring it out. Yeah. No sound yet. There we go.
Testing audio now.
Yes, we can hear you.
Testing audio now. Can you hear me?
Yes, we can.
All right, I got an acknowledgement from Jason that audio is good. So sorry about that. Yeah, this headset just upped and died on me. That was very unusual and embarrassing. Okay, let's continue. So we have a clustered index scan operator here for this particular query. And if I look inside the messages tab, logical reads, nearly 40,000 logical reads. So we did a heck of a lot of IO here. We scanned through the entire table. And maybe this is a situation, let's pretend that this is a situation that, you know what, we need to optimize this guy. We need to do better. So I'm going to copy this out just so that we have this. And one of the ways to approach or fix this that I've often heard is, well, hey, what will happen if we split this up into multiple queries? The application could go into SQL Server, just get the IDs of the inventory that we need, and then we'll go back again, and then we'll get all the other data points. What about that approach, right? I've heard this oftentimes from folks who don't really understand the storage engine very well, and understand the internals of SQL Server. But if you think about all of the different things that we just learned today, all the different things that I've covered about how we navigate B trees, about how we move through different index structures and constructs and stuff like that, you're gonna start realizing that this particular approach, which kind of from a logical perspective makes absolute sense of, yeah, just get the IDs and then we'll get the subset of data, may not be the best approach. It could work in certain situations, but in this example, I want to show you how it could be very detrimental. Remember that my data distribution was approximately equal all across the board here. So let's go ahead and implement this example or this approach. I'm going to create a simple temporary table with all the different with all the different IDs in a clustered key. And then we're going to insert into that temporary table I'm going to just grab inventory flat ID where model name is equal to rav4. And then we're going to do the full query once again, and I'm going to do an inner join back to that temporary table. Let's compare and contrast. Could help if I ran the whole thing. Okay, if I look at the messages tab, and I'm going to scroll back up just to show so that we have the prior numbers. So if I look in the messages tab, 596 logical reads, that's to read from the inventory flat table into the temporary table. So that's good. That's nice and lightweight. But then the join, hey, wait a minute. I have to go against all of inventory flat once again. Why is my logical reads identical? You know, that doesn't make any sense. Well, again, think back to the B tree structure. Think back to what we had to do here as far as, you know, how we navigate. So in this case, SQL Server, once again, did a full index scan. It went to the clustered index. It didn't even make use of our non-clustered index. Well, Andy, why don't you just add in all of those other columns into that non-clustered index? Well, that goes against the, you know, the key question of, do I want to add in every single other column that exists in a non-clustered index into the definition of a non-clustered index? The answer might be it depends, but the thing is that you know, kind of eliminates one of the trade-offs, or one of the benefits of a non-clustered index, is that usually it's a narrower construct where we only have a subset of what we typically need. Remember, this is an example of a query in my workload that I need pretty much everything out of this table. So is it worth it for me to go ahead and add in every single other column into that non-clustered index? Let's pretend in this example, for sake of discussion, that the answer is no. It is not worth that trade-off. So this approach of going back and getting that data again is really not going to help me. And it's not going to help me from an I/O perspective either. Even if I did add in all those other non-clustered all those other columns into that non-clustered index, because that's going to basically make that non-clustered index the same size of that clustered index. So really, how much benefit are we going to get? But again, everything in SQL Server is a bit of a trade-off. Now, some of you might say, well, wait a minute, Andy, you did a join here. You know, doesn't a join also retrieve the data? You know, could you use a different approach? Well, all right, fine. I'm going to do an exists check here instead, you know, and say, hey, will anything different here happen in this particular example? Well, in this particular example, no, we have the same, you know, index scan operation occurring here as well. And from an I/O perspective, I still have to go through all of the inventory flat table once again. So unfortunately, no, that doesn't help us out here. Because again, now that we have a better understanding of how SQL Server and the storage engine must navigate through the B tree, you know, when we're looking for model name and looking for those IDs, even though I have a discrete list of those IDs now, those IDs may be all over the place in the final table. That's one reason why I have to scan through the entire thing. The other alternative would be to do over 100,000 individual seeks. And we've already shown you how, you know, multiple seeks will usually be more terrible than just one single scan, right? So hopefully, you know, this gives you a better appreciation of this kind of common scenario, because I've heard this approach be proposed many, many, many times over. So now you have a good example of why, from a SQL Server perspective, this probably is not a good approach. I say probably because, again, there may be data distributions where this approach may work just fine. Or you can go ahead and add in the additional supporting columns into your non-clustered index to change that around. But again, for the sake of our discussion, we're going to pretend that the answer to that one happened to be no. All right, so if you want to go check out some of the other optional stuff, again, all of my scripts are up on GitHub. There's also optional stuff of what happens if we go parallel or not parallel. But in the interest of time, I'm going to skip over that for this purpose. And then that pretty much kind of wraps things up as far as the demos are concerned. So with that, I just want to leave you with a handful of different parting thoughts. I want to encourage you to widen your perspective. Think not necessarily just about your individual query when you're query tuning or writing code, but think about everything else that's on the server. Like that buffer pool, for example, is a shared resource, you know, that everyone has to deal with, right? So, you know, your production environment may be such that your database may be one of 100 databases on a given server. And even though that server may be very, very powerful with really nice specs, it's still 100 or 99 other workloads that you have to contend with. You all have to share that buffer pool, right? And try and be mindful of the unseen work that's being done when you fulfill a query. You know, some folks that I talk to that are less experienced will say that, oh, this query only returns 10 records or 30 records. I don't care about that. That's fast. But here's the thing. What did it do behind the scenes? How much heavy lifting had to actually occur in order to get those just 10 or 15 records? Did I have to parse through hundreds of megs or even gigs of data to finally get down to that? And that's why I'm encouraging you to look behind the scenes and have a better understanding of how SQL Server and the storage engine works. All right, so with that, here's the long promised GitHub URL that I have up for you. My contact information here is what is here as well. So with that, let me go check out and see if we happen to have any questions.
So it seems like at the moment there are no new questions, but
So hold on for a second. I am actually not getting your audio now.